Hi class, in this screencast I want to continue on our discussion and lead you into stoichiometry, what limiting reagents are, and finally the percentage yield calculation. So this screencast, similar to the previous one, I'm going to show you a lot of math in conjunction to the PowerPoint slides that I have posted earlier on Blackboard. So let's start with stoichiometry and take a look at what exactly it means. Stoichiometry is basically a term that explains, that relates the number of moles of the products and the reactants to each other as well as to among themselves. So what I mean by that is, let's say you have a generic reaction. Maybe make it as simple as sodium hydroxide is reacting with H2SO4, and that gives you Na2SO4 and water. And just for the sake of argument, I'm going to I'm going to write the H2O as HOH. Obviously, you're going to need 2 moles of NaOH for the reaction to take place in order to balance it. And you're going to need, likewise, 2 H2O will get generated. So if you were to read this in terms of stoichiometry, that would mean that 2 moles of sodium hydroxide react with 1 mole of sulfuric acid to generate a mole of sodium sulfate and 2 moles of water. So this can be viewed pretty similar to your recipe, your regular kitchen recipe. Actually, you can perhaps envision maybe your favorite recipe for pancakes. Okay, so let's see, what do we need? Let's say I want to prepare 4 pancakes, and my favorite recipe that my grandma wrote, according to that, I need 1 cup flour, maybe put 2 eggs, let's put half a teaspoon vanilla essence, what else? Milk. 1 cup milk. Okay. Alright, so I know that if I have a cup of flour, I must put 2 eggs, I must use a cup of milk and half teaspoon vanilla. And together, these are going to give me 4 pancakes. So tomorrow, if I wanted to make 12 pancakes, you perhaps can envision that you must multiply the entire recipe by 3. That means you will need 3 cups of flour, 6 eggs, 1.5 teaspoon of vanilla, and 3 cups of milk. So realize that there is a relationship that is established between the ingredients and the product. And same goes in case of a chemical reaction as well. There is a relationship that is existing in terms of moles, in terms of the ingredients, which means the reactants, and the product, in this case sodium sulfate and water. So as long as we keep that constant in accordance to the balanced chemical equation, we should be set. And this is the idea that I want to take forward in the next example that I'm going to give you. Alright, let's consider another reaction. Perhaps 2 sodium hydroxide is reacting with chlorine, and that gives you NaOCl. Can you remember what is the name of this compound? It is sodium hypochlorite, and sodium chloride is formed as well as water. So realize, if I were to, this is a balanced reaction, so if I were to read the information, I would say 2 moles of sodium hydroxide react with a mole of chlorine to give you 1 mole of sodium oxychloride or hypochlorite, 1 mole of sodium chloride, and 1 mole of water. So now if you wanted to figure out how much chlorine gas would you require to carry out a reaction, so how many grams of chlorine would you require for a given grams or for a given amount of sodium hydroxide, you can say that, well, your reaction in a balanced sense is that 2 moles of sodium hydroxide corresponds to a mole of Cl2. And so if you can figure out the grams of sodium hydroxide and relate that to the number of moles, let's put a number to this. Let's say you're given 120 grams of sodium hydroxide. Okay, so suppose the question is that you're given 120 grams of sodium hydroxide. How many grams of Cl2 would you require for the reaction to take place? So your first step should be to convert the grams of sodium hydroxide into moles of sodium hydroxide, and like I said earlier, the best way to do that is to divide the grams by the molar mass of the compound. In this case, that happens to be sodium hydroxide, since we know that 40, 23 for sodium, 16 for oxygen, and 1 for hydrogen. When you add them together, it comes out to be 40 grams. Essentially, we are talking about 3 moles of sodium hydroxide. And in accordance to the stoichiometry, 2 moles of sodium hydroxide corresponds to 1 mole of Cl2. So let's just incorporate the stoichiometry as well. Since 3 moles sodium hydroxide is what I have, and 2 moles sodium hydroxide is equivalent to a mole of Cl2, I can say that in this entire process, basically 3 divided by 2, that means 1.5 moles of chlorine will be required. And since it's a Cl2, you can perhaps envision that 2 times 35.5, that will be the mass of chlorine. So that happens to be 71. 71 grams of Cl2 corresponds to 1 mole of chlorine. So the mole and mole cancel off. 71 times 1.5, that should give you the grams of Cl2 gas that will be required in this process. And that comes out to be 106.5 grams total. And that is the answer to this question. Okay, continuing on from slide 22, we have the same equation. 2NaOH plus Cl2 gives you NaOCl plus NaCl plus water. And the first question is, how many moles of chlorine are needed to react with 2 moles of NaOH? So like I said, the one and only thing that you need to verify is whether the equation is balanced or not. And in this case, it is balanced because you have 2 sodiums. We have 1 here, we have 1 here. We have 2 oxygens. We have 1 here, another in water. 2 hydrogens, both of them culminating in H2O. The Cl2 right here is distributed between sodium chloride and NaOCl. The equation is balanced, so this is an information that you can simply read off of the reaction. And so for 2 moles of NaOH, you require only 1 mole of chlorine. So the answer to that is 1 mole of Cl2. The second question is, how many moles of chlorine are needed to react with 3 moles of sodium hydroxide? So of course, now we have a relationship. Essentially, we have 3 moles of NaOH, and according to the stoichiometry, I know that 2 moles of NaOH reacts with 1 mole of chlorine. So I'm just going to put it in the dimensional analysis method. That will give me an answer of 1.5 moles Cl2. The third question is, how many moles of NaCl are formed? Guess what? We have, when there is no number, that basically means that the number is 1. So we have only 1 mole of NaCl that gets formed in this reaction. And the last question is, if you start with an excess of chlorine and just 5 moles of NaOH, how many moles of water can you produce? So now we are looking at a relationship between sodium hydroxide and water, for instance, which is 2 to 1. So realize that irrespective of the fact if you have an excess of one particular component, if you are limiting the amount of the other component, then the products are going to be limited as well. This concept is also called as limiting reagent, which I'm going to discuss in a little bit more detail than what we are going to leave with in this particular problem. So since limiting reagent, since in this case we have limited the amount of sodium hydroxide, that is what is going to decide the amount of water that gets generated. So here, since it's sodium hydroxide, you would say that the given amount of sodium hydroxide is 5, and 2 moles of sodium hydroxide is giving you 1 mole of water. That's the stoichiometric relationship. The mole and moles cancel off, and you're left with 2.5 moles H2O. And that is your final answer. Okay, we have more questions on slide number 23, slide 23, and as well as 24, which is where we have more questions. So let's take it one step further. The question is, how many moles of sodium hydroxide are needed to react with 25 grams of Cl2? So it's given that you have 25.0 grams of Cl2, and the question asks you how many moles of sodium hydroxide are required for this reaction. So this is similar to what I started the discussion with, the relationship between the two reactants. What is that? So the first step should be, because you have grams here and I'm asking in terms of moles, your first step should be to convert the grams into moles, and that can be done very easily by simply dividing the grams by the molar mass. So in this case, since it's Cl2, you're going to divide it by 71, and that will give you the moles of chlorine. So let's go ahead and do that. And that comes out to be 0.352. Significant figures, the given data is 25.0 molar mass. In this case, since I just am using 71, that is the least of the two, so you're going to stop after the second one, but realize the rounding up, rounding down, all of that is done at the end, not in the middle of a calculation. Now I want you to basically put in the stoichiometric relationship. And according to the stoichiometric relationship, a mole of Cl2 is going to require 2 moles of NaOH. And so moles and moles will cancel off, and you will get 0.704 moles of sodium hydroxide. And the last step will be to convert the moles into the grams, and so for that you'll need to multiply it by the molar mass of sodium hydroxide, and that's what I'm doing in the last step. The moles and mole cancel off, and you're going to be left with approximately 28 grams. I think it'll come out to be 28.16. Let me just check that. 40 times 0.704. Yep, 28.16 grams of sodium hydroxide will be required for this reaction to go successfully. So going back to the questions, the answer to the first part, where we were asking for the moles of NaOH, that would have been just 0.704 moles. And the answer to the second part, where it asks for the grams of NaOH, that will be 28.16. All right, let's then discuss limiting reagents. What are limiting reagents? Limiting reagents, sometimes also referred to as limiting reactants. The extent of the reaction as to how much of the product will be obtained of course in accordance to the balanced reaction, this is decided by the limiting reagent. Like I gave you an example in the last question, even if you use an excess of 1, since it has to be in a specific ratio, that ratio will be followed, and so whichever amount is lesser in quantity, that is the one which is going to act as a limiting reagent. Whatever is the excess reagent, so even if you had a boatload of a particular reactant, the extra is going to just remain in the solution and do nothing. So this is similar to saying, let's say you wanted to make salad, okay? You wanted to make fruit salad maybe. And your mom's favorite recipe expects you to use, let's pick any two fruits, maybe bananas and apples. All right, that's what I want to use. And of course we'll use cream, but the ratio of the bananas and the apples, it has to be in 6:4, that ratio. All right, so for every 4 apples you need 6 bananas. Now when you go to the refrigerator and you try to get all the fruit out, you see that there are only 2 bananas or 2 apples, and there's maybe a dozen bananas, so you have 12 bananas. All right, my question is, how much can you use and how much fruit salad would you generate? Well, realize since the number of apples which is lesser, you cannot use any more than 3 bananas in this particular case. So for every 2 apples you will utilize only 3 bananas, and the remaining 9 bananas are just going to simply be returned back in the fridge. And if you think about the apples, they are getting completely exhausted in this entire process. So whatever is the limiting reagent, that gets used up in the reaction. Whatever is the excess reagent, that just remains unreacted. Okay? All right, so I have a question here, which is the synthesis of titanium, which is in the solid phase, and I'm treating that with Cl2, 2 Cl2s to give you TiCl4, which is also solid. This is gaseous, and then some information is provided. The question says you are given 1.8 moles of titanium. You're given 3.2 moles of chlorine. What is the limiting reagent? So that's what you have to figure out. What is the theoretical yield of TiCl4? Now, the concept of theoretical yield is basically the maximum yield that is theoretically possible, provided the reaction conditions, the isolation, all of that is completely ideal situation. Okay, so theoretical yield is just the maximum yield that is possible in accordance to the limiting reactant that we are using for that particular reaction. So your first step here should be to figure out the amount of product that you're going to get utilizing both of these starting materials. So the first case is the case of titanium. Realize this is a balanced equation. You have 1 titanium on each side, and you have 4 Cls. You have 4 Cls on the right hand side, so we are good to go. Titanium, it says that I'm given 1.8 moles of titanium. Now, since the ratio of titanium and TiCl4 is 1:1, if you have 1.8 moles of titanium that is given, you perhaps can envision that it is going to yield 1.8 moles of the TiCl4. So the moles of titanium will cancel off and give you 1.8 moles TiCl4. Okay, now for the case of Cl2, you're given that you have 3.2 moles of Cl2, and for every 2 moles of Cl2 you have 1 mole of TiCl4. So 2 moles of Cl2 is giving you a mole of TiCl4, which is your product. Mole of Cl2 and mole of Cl2 cancel off. 3.2 divided by 2 gives you 1.6 moles of titanium tetrachloride. What does that mean? That means that with the amount of chlorine that is given, essentially in this particular experiment, the amount of chlorine is going to limit the amount of TiCl4 that will be generated. So what becomes your limiting reactant? The 3.2 moles of Cl2 becomes your limiting reactant. And what is your theoretical yield? Your theoretical yield essentially is the 1.6 moles of TiCl4, which is your theoretical yield in moles. Now, if somebody asks you what is the theoretical yield in grams, what do you do then? Then you will need to convert the moles that you have obtained into grams. And the best way to do that is essentially multiply it by the molar mass. So titanium you can read off from the periodic table as to how much it weighs, and the chlorines are 35.5. So figure out the molar mass that you have for TiCl4 and simply multiply the number of moles by that to get the final answer in grams. But here you were supposed to report the answer in moles, so we're good with what we have. Okay, let's move forward. I think it's slide number 26, and I have another slide 26. And I have another question here. The reaction is between aluminum and chlorine, and that gives you AlCl3. Notice this reaction is not balanced now. In order to balance it, you need a 2 in front of aluminum and AlCl3, and that would make 6 chlorines. That means you need a 3 Cl2. You're given 0.552 moles of aluminum. You're given 0.887 moles of, it really should say Cl2, not just Cl, because Cl doesn't exist as a monoatomic, but rather a diatomic molecule. And again, the question asks you what is the limiting reagent, and it asks you for the theoretical yield in moles. So similar to the previous question here. So hopefully you realize we already have verified and balanced the reaction, and that should aid you in understanding the stoichiometric relationship between aluminum and AlCl3, which is 1:1, because you can safely say 2 moles of aluminum is giving you 2 moles of AlCl3. So you can perhaps envision that if you're given 0.552 moles of aluminum, since 2 moles of aluminum gives you 2 moles of AlCl3, they're going to cancel off, and you're going to end up with just 0.552 moles of AlCl3. So that's my Ty with respect to aluminum. And if you consider what's going on with Cl2, you can safely say 0.887 moles of Cl2 times, so 3 moles of chlorine is going to give you 2 moles of AlCl3. So again, realize we are writing the moles of AlCl3 that will be produced in terms of the reactant. So we can cancel that part out, and that comes out to be, in my calculator, 0.591 moles of AlCl3. So clearly, since 0.552 is the smaller of the two, that becomes the Ti or Ty, the theoretical yield, and the reagent that facilitates that, which is aluminum, is your limiting reactant. So a couple things here. Limiting reactant does get exhausted completely in the reaction. A limiting reactant will always need to be one of the reactants. It can never be on the right hand side. It has to be on the left hand side, one of the two. And also, as you are trying to figure that out, you must make sure that the reaction that you're beginning with is going to be a completely balanced reaction. Okay, I'm on slide number 27, which is this reaction that I'm showing you. Potassium, platinum, tetrachloroplatinate, potassium tetrachloroplatinate reacting with ammonia, 2 moles of ammonia to give you cisplatin. This molecule here is a currently known drug, clinically used drug for cure of cancer of ovaries, head and shoulders. This is also called as cisplatin. And it was discovered at Michigan State University, and it's going to give you KCl essentially as your byproduct in this reaction. That's what you're going to get. Now the question says that we have been given 10 grams of potassium tetrachloroplatinate, and we have 10 grams of ammonia. And the question asks you, which is the limiting reactant? So what is the limiting reactant? Is it potassium tetrachloroplatinate or is it ammonia? Which one of the two is the limiting reactant? And then it goes on to ask how many grams of the excess reagent are consumed and how many grams of cisplatin are formed. So realize that in this case I have already given you the molar masses. The molar mass of potassium tetrachloroplatinate is 415.08 grams per mole. For the case of ammonia, we have 17.04 grams per mole, and cisplatin that has 300.06 grams per mole. Now, as always, in order to determine the limiting reagent, your first step should be A, whether it's balanced or not. In this case, I'm letting you know that yes, this is a balanced reaction. If you want to verify that, you can do that by comparing the number of atoms of each kind on either side of the reaction. But the next step would be to basically figure out the moles that you have for each of the reactants, and then using the stoichiometric relationship, figure out the moles of cisplatin that will be obtained. So we are going to follow along the same thing as we have been doing. So let's figure out the moles of K2PtCl4. You have 10 grams. When you divide it by the molar mass, which is 415.08, you're going to end up with, let's just plug this on the calculator, 10 grams divided by 415.08 gives you 0.02409 moles. For the case of ammonia, you have 10 grams again, and I'm going to divide that by 17.04. So the reason why we do that is because the molar mass of ammonia is 17.04, and I got 0.586 as the moles of ammonia that are available. So if you were to figure out the moles of cisplatin with the given moles of each kind for K2PtCl4 and the case of ammonia, you can perhaps envision that 1 mole of potassium tetrachloroplatinate gives you 1 mole of cisplatin. So 1 mole of, I'm going to just call cisplatin, so it's easy for you to follow. So the potassium tetrachloroplatinate, that part will cancel off, and the first number you're looking for is 0.2409 moles of cisplatin are obtained. When you do the same thing for ammonia, realize that 2 moles of ammonia give you 1 mole of cisplatin. So moles of ammonia cancel off, and the moles of cisplatin that you will get in this case will be 0.2934 moles of cisplatin. Of course, the first one is smaller, and so that is going to act as your limiting reagent. So the answer to the first part is that potassium tetrachloroplatinate, that is your limiting reagent. The second question is how many grams of excess reagent are consumed? Realize if K2PtCl4 is the limiting reagent, that means that ammonia is your excess reagent, and if that is the excess reagent, then it's only going to react in a manner which is equivalent in accordance to the balanced chemical reaction. So if you have only 0.02409 moles of K2PtCl4, essentially, since the relationship between these two is 1:2, one can safely say that 0.02409 moles of K2PtCl4 and 2 moles of ammonia are reacting, so it will require 2 moles of ammonia for the reaction to go to completion. So basically 0.04818 moles of ammonia will be consumed. And if you want to convert the moles of ammonia to grams of ammonia, you will simply multiply it by the molar mass, which is 17.04. That's what's given to you. So you're going to simply say 0.04818 times 17.04, and that gives you 0.00829. That many grams of ammonia are consumed. So that's the answer to B. And we are simply following the relationship between the two reactants in this case. Okay, the last question asks you how many grams of cisplatin are formed. Realize when we first started to calculate the moles of cisplatin that will be formed, we calculated that to be 0.02409. So if you just simply wanted to calculate the grams, just simply multiply this number by 300, and that will give you, and I'm multiplying it by 300.06 grams per mole. I'm doing that because that is the molar mass of cisplatin. So if you actually punch in those numbers on the calculator, and let's just do that, 0.02409 times 300.06. Yeah. And that comes out to be 7.228, 7.23, let's call that. That will be the answer to part C. So, I'm going to do a couple more problems that are on slide 28, 29, and 30th so that we exactly know what we are doing with this and where we are going with this. The next question here is that you have lithium oxide, Li2O, which is reacting with H2O, and it gives you 2LiOH. And the information given for you in the form of a mini case study is that lithium oxide is a drying agent used on a space shuttle. If 80.0 kilograms of water, 80.0 kilograms of water is to be removed, and you're given 65 kilograms of Li2O, which reactant is limiting. You're also given that the molar mass is 29.88 grams per mole, and the other one is 18.02. So for water, it's 18.02 grams per mole. This is a balanced reaction. Hopefully you can see that pretty quickly. Two Li atoms, 2 H and 2 O's. So basically you would be doing the same thing we have been doing. Calculate the moles of both the reactants. Use the stoichiometric relationship to see which one is going to be formed in a larger amount. So let's do that for the case of Li2O. That's 65 kilograms. So let's convert that into grams. So that's 65,000 grams, and 29.88 grams make 1 mole. 1 mole. So this is going to come out to be 65,000 divided by 29.88. and that comes out to be 2175.368 or 37. So use the significant figures appropriately, but that many moles of Li2O is what is present. When you do the same thing for the case of water, you would say 80,000 grams of water, and you'll divide it by 18.02 grams to convert it into the moles, and that will come out to be 18.02. That will come out to be 4439.5. Those are the moles of water. Realize both of these give you 2 moles of LiOH. So if you want to, you can, in order to be rigorous, you can say that 1 mole of Li2O gives you 2 moles of LiOH, or not, because both of those have exactly the same ratio. And so that gives you total moles of LiOH that you will get will be 2175.36 times 2 is equal to 4350.7 moles of lithium hydroxide will be generated. Okay, likewise, when you do that for water, when you multiply that by 2 to get the moles of lithium hydroxide, you're going to get essentially 88. So 4439.5 times 2, that comes out to be 8879. Hopefully you can see, as we have seen previously, that you are getting less number of moles using lithium oxide, and so your limiting reagent is going to be lithium oxide in this case. Okay, I'm going to go over the last concept in the screencast now, which is determination of percent yield. And this is a concept that those of you who have to take organic, you guys are going to use that on an everyday basis. Every single time you go to the lab, so 20 to 10, 20 to 11 candidates, please pay attention. Realize that when we run a reaction, it's not really mandatory that we are going to get good yields or good amount of product as a rule. A lot of times it's a possibility that handling of chemicals, the way we add it, too quick, too slow, that kind of changes the outcome. And so percent yield is a tool that helps us realize how successful our reaction was. Also realize that the percent yield is dependent on, of course, the amount of reagents that you use, and very specifically the amount of limiting reagent that is available for the given reaction. So if you were to define percent yield, you can say that a percent yield is equal to the actual yield or experimental yield that you get in reaction divided by the theoretical yield times 100. Like I said, theoretical yield is the maximum, the 100% that is possible, but in reality, that is not true. So please realize that your percent yield can never be more than 100%. If it is, that means you created matter, and that is not possible within the rules of science. So the question here is, CH2Cl2 is prepared by reaction of methane and Cl2 giving HCl. So the reaction given is CH4 plus 2Cl2, and that gives you CH2Cl2 plus 2HCl. It is a balanced reaction. How many grams of dichloromethane result from the reaction of 1.85 kilograms of methane? We are asking grams of dichloromethane. If the yield is 43%, so the percent yield is given to be 43.1. What that means is that the ratio of actual yield by theoretical yield is given as 43.1, or one can say that 0.431 is equal to actual yield divided by Ty. This is something which can be written based on the equation that is provided. Now, This is a balanced equation, and you can perhaps read that 1 mole of methane gives you 1 mole of dichloromethane. So realize if you're beginning with 1.85 kilograms of methane, then that means 1.85 times 10 to the power of 3. So 1850, that many grams of methane are available. And if the molar mass of this is 16, so if you divide this by 16, you would be able to look at the moles of methane that are available. So let's go ahead and do that. 1850 divided by 16, that gives you 115.625. Those are the moles of methane that are available. And realize that whatever is the number of moles of methane, same is the number of moles of dichloromethane that are going to be generated. So if the moles of methane are given, then that would mean that the same number of moles are going to be generated for dichloromethane. So we already have the theoretical yield of dichloromethane in moles. In order to see the grams, you simply, all you have to do is you need to convert that into the grams by multiplying the mole number by the molar mass. And for the case of dichloromethane, you can use 12 for carbon, 1 for hydrogen, and 35.5 for chlorine. And so that will give you 85. So now if you multiply the 115.625, if you multiply that number by 85, you're going to get 9828.125, that many grams of CH2Cl2. Please realize this is the theoretical yield, and our aim is to determine the actual yield. So now we are going to plug in this newly found number into my reaction to be able to get the final answer in actual yield. So I'm going to further multiply this number by 0.43. So this number times 0.431, and that's going to give you the actual yield will come out to be 4235.9. Report only 3 significant figures, so you can write that as 4.24 kilograms or 4.24 times 10 to the third grams as the final answer. With that, the main concepts in this chapter are over, and we'll go over the worksheet in class.